problem 4.28. For this problem, we will assume that the dielectric fluid reaches an equilibrium when the total dielectric force is equal to the total weight of the fluid above the surface level. So the dielectric force is given by F equals negative 1/2 v squared dc dx. For the capacitor in figure 4.32, it is composed of two coaxial cylinders, meaning that we can use the formula for a cylindrical capacitor. C is equal to epsilon L times the natural log of the outer radius divided by the inner radius. So epsilon could be epsilon naught for air, could be epsilon naught times epsilon R for the capacitor that's for the portion that's filled with oil. In fact, for this term, this is the rate of change of capacitance. We need to determine how much does capacitance change when it gets filled with oil, and that change is literally just epsilon minus epsilon naught. Furthermore, this is rate of change with respect to height. The height of the oil, again, look at the figure, the height of the oil goes along the L direction. So we can say that the rate of change of capacitance is epsilon minus epsilon naught times the natural log of B over A. And consider that epsilon is equal to epsilon naught times epsilon R, and that epsilon R minus 1 is key E. So we can say that for this capacitor system, the dCdH term is equal to this right here, epsilon naught key E times the natural log of B over A. Now, since we're going to assume that this is an attractive force, we're not going to worry about direction, and so that's why we're not including this negative sign. So the total force is 1/2 v squared times dc dx, which gives this term right here. Next, we say that that force should be equal to the weight of the oil that's been lifted above the surface. So that oil has a density of rho and a volume of H times the volume of the outer cylinder minus the volume of the inner cylinder. The volume of the cylinder goes as pi r squared. So for this, I pulled a pi out of both of these terms, and we're left with the volume of that cylinder is equal to H times pi times B squared minus A. So again, we are setting the weight equal to the dielectric force. The weight is equal to rho, that is the mass density, times G times the volume, is equal to the dielectric force. And so we should simply take this formula and solve for H. H is equal to epsilon naught key E natural log of B over A, all divided by rho G pi B squared minus A squared. That was quite a mouthful.